Hello, everyone. Thank you for coming to our talk. We're super excited to tell you all about what we're building with SkyRL, our modular RL library for language models. As Matt said, I'm Tyler. I'm a PhD student at UC Berkeley. This is Sumanth, an engineer at Anyscale. And of course, we're presenting on behalf of the much larger SkyRL team and all the wonderful open source contributors who have sent a lot of PRs to this SkyRL project. So in today's talk, we're going to tell you a little bit about the motivation behind why we built SkyRL, why we built this RL framework, the design and architecture and what this framework does. And then finally, we'll go into looking at some of the next steps and roadmap we have planned. So first, why SkyRL? So the way I want to motivate this is by walking through a maybe overly simplistic view of the eras of applying reinforcement learning to language models, focusing especially on the workload characteristics. Like what kind of system requirements does this place on the underlying infrastructure? So start with RLHF. Reinforcement learning from human feedback, where this workload often looks like single turn. So you're not giving the model multiple attempts to solve some problem. You present a prompt or a task to the model once. You're doing only text generation. So this is to contrast from executing tools in some external servers. And finally, relative to today's reasoning or agentic models, this was relatively shorter context and shorter rollouts. And so what this meant is it meant that it made a lot of sense to collocate and tightly couple training and inference. And the reason for this is that the workload on either was relatively small compared to, again, today's standards. And so the time to sync your updated policy model weights from the training workers to the inference workers, if you would place them on separate GPUs, ended up being a pretty significant portion of the overall training loop time. And so folks co-located these. They put training workers, inference workers on the same GPUs and like hot swapped between the two as you progress throughout the training. Next, we moved to reasoning. And actually, the workload looks, again, being overly simplistic, the workload looks somewhat similar to RLHF, with one main distinction in these characteristics being now the context and rollouts are much longer. So we're training models specifically to have these longer chain of thoughts. And so what that means is the inference phase starts dominating the training step time relative to updating the model parameters themselves. So still co-locating the two of these, but now we're feeling some pressure to want to scale up the inference compute more than what we have for training compute, which you can't do if you're tightly co-locating these two. And finally, we get to where we are today, where we're training agentic models. And really what that looks like in these characteristics means we're now doing multi-turn, not just giving the model one attempt to solve some tasks, but actually giving it many. We're going beyond just generating text from the model, but we're now taking that text, interpreting it as some action that we actually go and execute somewhere. So now there's more compute being allocated and time being spent to execute those actions. And even more so compared to training reasoning models, the context and the rollouts are only getting longer, especially because of this multi-turn behavior. And also, we have this third component we now add to our training loop, which are the environment servers themselves. As I said before, you now take policy model rollouts, interpret them as actions, and go execute them in these servers. And so really what this means is, as we've walked through these three eras, the system requirements have evolved and diverged pretty significantly from where we started. And so now it's time to start rethinking the RL stack design instead of sticking with this tightly co-located coupled setup. So what do we want from our RL framework? First, we want to support diverse backends. So for each of these components, your trainer, your inference engine, your environments, there are going to be many options. You may be used to using VLLM for your inference. You may use SGLang. You may use one of several of the popular training backends. And of course, environments are super diverse. There's a million people building a billion different environments. And so ideally, you shouldn't have, if you're adding a new environment, you shouldn't have to care what's going on about the inference component or the training component. You should be able to support these diverse backends without headache. The next is we want to utilize the best hardware. Best here could be defined by what's the cheapest hardware for each component, what's the most performant, what's the most available. We just want to be able to pair each component, which has different system requirements, with the hardware that's best suited to run it. And beyond the actual choice of hardware, it's also the scale that we want to be able to separately manage. So even if you're using the same accelerators for training and inference, maybe, as we said before, you want to use more for inference than you do for training. And so you'd really like this independent scaling behavior. And really what subsumes these first two bullet points is what I'm saying is we want well-defined public APIs. We want to modularize each of these components, set up well-defined, simple public interfaces between each of them. And what this is, this is just good software practice, but also, of course, it allows you to do the things we mentioned before. So if you come in and you want to add a new inference engine, that's fine. You don't have to worry about the training stack. You don't have to worry about the environment stack. You just have to implement the contract that's specified by this API. And finally, once we have these nicely modularized separate components, we want flexible control flow. We want this controller that sits above them that lets us specify algorithms or execution plans as some data flow graph between these components that lets us flexibly change the algorithm as we see fit. And so I've given you a lot of motivation about what we don't want, what we do want. So now let's get into what SkyRL is and what it looks like. So I'm going to start with a high-level view of the architecture of the training stack, and then I'm going to walk through the components one by one. So to start, you can see there's a few core logical components. We'll start with the trainer and generator, where the generator's job is really just to generate trajectories and rewards. That's it. So given some task specification, it presents that task to the model, and the model constructs some trajectory as you iterate between using the inference engine and the environment. You score the final result as some reward, and you pass it over to the training stack. And I should say, the generator could be fully agnostic to the fact that there is a training stack. Maybe you're not training, you're just running evaluation, or you're trying to generate some SFT traces to distill to another model. So the generator is agnostic to training. The training stack is going to take as input these trajectories and rewards, and its responsibility is purely to update the policy model parameters based on those trajectories and rewards. So again, it doesn't need to know that the generator exists. It just needs to execute its one function, which is updating model parameters. And then finally, we have the controller sitting above it. So I'm going to go through all these one by one, but in the interest of time, even that discussion is going to be fairly high level. So if there are more questions, we'll set some time at the end, and I'm also happy to chat afterwards. But digging a little deeper into the responsibilities of the controller and why it's nice to have is the purpose is to allow you to flexibly specify control flow between components. But what does that mean? So traditionally, folks are often training models synchronously with RL, meaning the rollouts used to update the model parameters were generated by the most recent version of the model. But when you start placing training and inference on separate hardware, you'd really like to keep both of those, all of that hardware well utilized at the same time, which means you've now broken out of synchronous training and you're doing some asynchronous training. But the way that that's expressed is in this controller. You can express this flexible control flow of instead of the trainer waiting for the generator to complete its rollouts. Instead, maybe the trainer is just pulling on some buffer that the generator is pushing to. And so that's specified in the controller. This is also where you would specify things like where each component is placed on the hardware you have available and the scale, how much hardware it uses. This is where you could define the algorithm. So let's say you want to update the advantage estimator or the loss function. It doesn't really change the trainer. That's still mostly just doing forward and backward passes and updating the optimizer step. This lets you provides you some custom hooks that you can come in and change some of the algorithm details. And then, of course, the actual resource spin up and tear down itself is handled by the controller. Next to the trainer, like I said, it gets trajectories and rewards, updates model parameters. It's pretty simple. So I want to take this moment to just highlight some of the features that exist in SkyRL today. So we have first-class support for using FSDP or Megatron training backends. As a rule of thumb, I think what's most common among our users is FSDP is kind of the catch-all training backend that folks use, and Megatron is often for those who want to make use of the 5D parallelism that it provides, especially for larger scale MOE models. Although we have, again, well-defined APIs between each of these components. So if you want to bring your own training backend or think you can implement it better than we or others have, you can always implement in this interface and bring your own backend. In SkyRL, we support co-locating the training and inference engine workers, like we mentioned before, or decoupling them and placing on separate hardware. And just to rattle off some more of the features, you can do LoRa training, you can do large-scale MOE, you can do anything from training on some single GPU co-located training and inference to some decoupled training and inference across multiple nodes with 5D parallelism as well. And so I just want to say this is a component that's not often modified by users because most of these like training fundamental components are typically sufficient for most workflows folks are doing. So maybe the details here aren't as important because many folks come in and modify the generator, which we'll talk about next, without really needing to care about what's going on in the trainer. So the generator, as I said, generate trajectories, compute rewards. And really what you can think of this is the component that captures the agent loop, which specifies the flow between the inference engine to get model rollouts and the environment to go execute those rollouts and get some environment feedback, get the observations and rewards. For the inference engine, SkyRL standardizes on the OpenAI API. So we support VLM and SGLang out of the box, but if you have some custom stack or some fork of these that you want to use, you can plug them into SkyRL, just spin up a server, pass it a URL, and you can start training with it, no problem. The environment, since this is perhaps the most often customized component, I want to spend a minute digging into this a little bit deeper. It's very common, folks, they want FSDP or Megatron, they want VLLM, they're used to these things. They really just want to come in, tune the algorithm, define a new task, and train for that new task. So I want to take a moment to poke through a few modes in which folks do this. For a category of simple environments, you could think of this as web search or a text-to-SQL task or some Python interpreter executing bash commands. For the simple category of tasks, we provide the SkyRL gem. It's a super simple gymnasium-based interface that will be familiar to folks who've worked in RL, where you're mostly focused on this method step that lets you, step through actions in the environment. I'd say one nice feature about the SkyRL gem is the concept of reusable tools, where if I've defined this search tool or a text-to-SQL tool, it's like super easy for some new user to come and build their own task, but make use of that tool just within the framework. And also we have our own zoo of reference tasks to build on. So if you're working on something in the space of coding agent, search agent, SQL agent, these are things where the tooling is already implemented for you in SkyRL. The one other mode I want to mention is maybe you don't care about the Gymnasium API. Maybe you don't think it's great, or maybe you've already implemented your environment, but it's not implemented in the API. So the natural question is, do I have to find a way to cram my environment behind the Gymnasium API? And the answer is no. Our goal is to prevent you from needing to cram anything into anything. It should be smooth. The idea being that if you've implemented your environment in which you're making OpenAI API compatible calls to some inference engine to get rollouts, and you have a way of parsing those rollouts and executing them in your environment, then really all you need from us, from the SkyRL stack, is the base URL to the OpenAI endpoint, and you can typically just stack your environment right on top of the training stack. So as demonstration of this, we have a few examples in the repo, like integration with Prime Intellect's Environments Hub, or Terminal Bench, or Mini Suite Agent, or the Search R1 recipe. These are examples where, as I said, not implemented in the Gymnasium API, but just stacked directly on top of SkyRL. So I'll conclude the discussion of the training stack just by saying that really the core philosophy is enabling folks to come in and make whatever modifications or extensions or swap outs that they want in each of these fundamental components with as minimal developer burden as necessary, because I still think we're in a regime where the system requirements are evolving quickly, and so there's still a lot of exploration and innovation in each of these layers. So the goal is to be able to hack at a small scale and get your environment running, and then scale that up to a many-node training run when you'd like to. So with that, I'll hand it off to Sumanth to talk a little bit more about the agent side. Go ahead.
Thanks, Tyler. So I'm now going to talk more about our work in training on real-world agentic tasks. Now, some examples of these are deep research, where the agent can use Google search and web scraping tools in order to answer complex user queries. There's computer use, where the agent can use mouse or keyboard tools in order to click around a computer screen to accomplish some task. There's also the more popular Suite task, where the agent can use bash and file editing tools in order to solve issues in a GitHub repository. There's a bunch of components that go into implementing such complex tasks. And for comparison, I'm going to take 3 tasks. One as simple coding or math for reference, one as the deep research task, and another as the Suite task. Now, the tools you're going to be using for each of these tasks are different, like I mentioned before. For simple coding or math, you might use something like Sandbox Fusion from ByteDance, which will execute LLM-generated code with maybe some simple process isolation. For the deep research task, you'll have search as well as web browser tools. And for the suite task, you'll have a bash as well as a file editor tool. There are differences in environment scaling across these tasks. And by environment scaling, I'm referring to how you parallelize environment interactions when you're given a large batch of trajectories during training. So for example, with the simple coding or math task, you could maybe scale it simply with Ray. For the deep research task, your tools are probably calling an external API, both search and web browsing. So maybe you scale that by implementing some smart caching in your tools. For the suite task, you could implement scaling by maybe running a large number of containers in Kubernetes. There are differences even in the agent scaffold that you might use for these tasks. So you might use a simple React agent scaffold for the coding, math, or deep research tasks, whereas for the suite task, maybe something more specialized, like the OpenHand scaffold. There's also differences in dispatch, and by dispatch I mean how exactly you handle scheduling and executing a large number of trajectories concurrently. For the coding or math task, as well as the deep research task, environment execution can be cheap, so maybe you just execute all trajectories concurrently in an async fashion. For the suite task, you could implement something more involved, like a 3-stage async pipeline, which I'm going to get to later. And finally, you have an agent stack, and ideally you run it in multiple generation contexts without changing any of the code you've written for tools and the environment, etc. So these are some of the components that go into implementing these tasks. And taking a step back, if we go back to the RL system overview diagram that we saw before, we broke down the generator into 2 components, the environment as well as the inference engine. But like we just saw, there's a lot of details for complex tasks around orchestration, like dispatch, environment scaling, etc., that are not quite captured by just thinking about environment instances for a trajectory. So the Gymnasium API itself, which is really concerned about how exactly you've defined the environment and how you're thinking about environment interactions at a trajectory level, that is not enough when you're actually implementing these real-world agentic tasks. So ideally, we have a layer that can manage both of these components, and we want one layer for managing overall trajectory generation for agentic tasks, or an agent layer, and we've built such an agent layer in SkyRL. Okay, so I've got a high-level system overview here for how SkyRL's agent stack has been built. At a basic level, you have this agent runner class that is concerned with just managing generation for a batch of trajectories. It's going to use some specified dispatch logic to dispatch generation to these trajectory instances. For each trajectory, you can also specify a list of tools the LLM has access to, as well as the agent scaffold you want to use for this task. Typically, you might also have an environment server that's running that's actually going to be executing these LLM actions. Overall, this agent layer, SkyRL agent, is managing trajectory generation and providing us with building blocks for the 2 components we looked at, orchestration and the environment. And so we want to allow researchers to do things like bringing their own agent scaffold, running generation in any context. So that's different training backends, or maybe just an OpenAI compatible API for evaluation. We also want to be able to support improving just the dispatch logic for a given task, and maybe even change the environment sandbox for a task, etc. Okay, so this is how the SkyRL agent stack will fit in with the training stack that Tyler just talked about. We standardize around the OpenAI API. So as you can see, really nothing changes when we're looking at this diagram. We've plugged in the agent stack into the generator. And during training, in the beginning, the trainer would send a batch of prompts in the OpenAI conversations format. And this is going to be handled by the agent runner to generate trajectories. In each trajectory, we'll be making calls to the inference engine, again, in the OpenAI API format. And then finally, once generation is done, the agent runner will send back the final tokenized trajectories and rewards to the trainer. Okay, I want to spend some more time now talking about dispatch and efficient dispatch strategies for different tasks. Like I mentioned before, dispatch is around how exactly you schedule and handle concurrent generation for a batch of trajectories. For the computer use task we looked at before, typically you're executing LLM actions in a VM instance, and you can also reuse the same VM instance across trajectories. You're also resource constrained typically, so maybe there's this fixed number of VMs you can run at the same time. So what you might do if you're trying to scale to a large number of trajectories is use this async fixed pool strategy at the top, where you are reusing a small set of VM instances across a large number of trajectories. For the math, coding, or deep research task, environment execution is really cheap, right? These are API calls, or maybe this is just executing LLM code in a separate process. So you could scale by just executing each trajectory at the same time concurrently in an asynchronous fashion. For the suite task, when you're managing this execution yourself, so when you're managing running containers for each trajectory yourself, we've found that the initialization stage, where you're just setting up the container, the actual generation phase, where you're running the agent loop, as well as the evaluation phase, where you are maybe running some tests to give some final reward to the LLM. Treating each of these as separate stages and then overlapping them concurrently in an asynchronous 3-stage producer-consumer pipeline actually leads to a much better utilization. And we've found that this is 4 to 5x better than a naive batched implementation. So these are some things you can do with SkyRL agent, which is figuring out the right dispatch strategy for a given task. Okay, now I want to actually talk about a case study of implementing the deep research task in our agent stack, just to kind of show what details went into it, what are some gotchas, and what we've learned. So like I mentioned before, in this task, the agent has access to 2 tools, the search engine tool, as well as this web search tool. With the search engine tool, the LLM will provide some kind of search query, and the tool will return the top 10 results with some kind of short description. With the web search tool, given a URL, the web search tool will retrieve that content. And typically, these web pages can be long. There's also some kind of summarization logic, maybe by sending the content over to an external LLM so that you can manage context lengths efficiently. Okay, coming into more details for the tool implementations, we found that it's actually a bit tricky to get the tool details right. For example, with search, you would actually want to implement block lists. This is because you're typically training with some popular data sets, and the LLM can cheat its way to the final answer by going to websites like Hugging Face, where the data sets are hosted, or maybe Chegg. So you'd want to block list such websites. For the web browsing tool, you'd want caching so that you avoid repeated fetches for the same large web page. You'd also want to have some kind of chunking and summarization in each tool call so that you're able to efficiently manage context lengths properly. Okay, this is a snapshot of the SkyRL agent task YAML that you'd use for the deep research task. This contains some important information, like the agent class, which has details around the agent scaffold, as well as the actual agent loop implementation. There is the task itself. The task class contains details around, say, evaluation and maybe some custom instructions. There's also the list of tools that the LLM has access to that you can just specify in the YAML, as well as the particular dispatch strategy that you want to use right now for this round of generation. Okay, this is an example of how you use the task YAML. So you would simply instantiate our auto agent runner API, and then pass in the agent YAML, and once you have this agent runner object, you would just call .run on it with the data set to get your final generated trajectories. Now, I won't go into too many details here, but these are some reward curves that we got with the agent stack. with 2 backends, with the SkyRL training stack as well as the World backend. This is just to show that we've validated training, and you get to use these tools now out of the box. There's a lot more details around the recipe, around like how we got a good data set for the base model we used, and that's all in the blog post right here. Okay, I want to put one more point here on the agent stack. We've also validated training on this vBench task. So this is like a recent training run with the train reward curve as well as the validation reward curve that I'm showing here. We trained a Qwen 332B model on the R2E gem dataset, and we used like an improved version of the open hand scaffold. The evaluation accuracy for the baseline, which is a part of the DeepSpeed recipe, was 28%, while with similar settings with our improved tools, we're actually able to achieve like 33% evaluation accuracy at the same number of steps. This is to show that we've validated training. So we've done like training for 2 of these complex tasks, and you get to use these great set of tools out of the box with our agent stack. Okay, so that's all on the agent stack. I also want to talk a bit about the SkyRL roadmap. Some recent releases that I want to highlight are SkyRL TX, where we're actually providing this package that allows you to run a Tinker-compatible API on your own hardware. We also recently shipped LoRa support so that you can train efficiently with lower memory usage while achieving similar accuracy as full fine-tuning. There's a lot of features we're also working on right now. Some of them are better asynchronous training so that you can have in-flight weight updates, and also better memory management so that you can have summarization in the training loop while also still maintaining on-policy training. If you're interested, we recently made a Slack workspace. If you're thinking about trying out SkyRL or just contributing to SkyRL, do join our Slack workspace. The link's right here, and we have a QR code right here in this page. Thank you.